Hi everyone, in this project I'm computing the arc length of an ellipse using numerical integration. Here's the ellipse that we will be using. Arc length means the total distance around a curved path. In real life, this is like measuring the distance around a racetrack. Since curved paths are hard to measure exactly, we approximate them using numerical methods. Imagine trying to measure a winding mountain road. You can't measure it with one straight ruler. Instead, you want to measure it in smaller pieces using segments. And that's exactly what n will represent in these graphs. It'll represent how many small pieces we divide the curve into. So here is the first graph. We're looking at left Riemann, trapezoid, and the Simpsons rule. For some reason, I can get left Riemann to show up on the graphs. The horizontal line right here represents a high accuracy reference value. So when n equals 10, the estimates are more spread out. That's like measuring the road using only 10 straight boards. But when n equals 20, the estimates move closer to each other, to the reference line, and when they're 40, they all get there. What's important is that as n increases, all methods converge toward the true arc length. But you can see that the Simpsons rule teaches the correct value much faster than the others. It reaches it much faster. Left Riemann is like measuring a curved road using straight wooden boards placed end to end. The trapezoid method improves this by adjusting each board based on both ends. Simpson's rule goes further. Instead of straight lines, it uses small curved segments, which match the shape much better. That's why Simpson's rule is more accurate in this graph. Now we have another absolute error versus n log. This graph shows how far each estimate is from the reference value. That's the error. The axes are on a log-log scale, which helps us see how quickly the error decreases as n increases. The key idea is the steeper the lines drop, the faster the method improves. So the left Riemann's error decreases slowly. Sadly, I wasn't able to pull it up. The trapezoid method decreases faster, and the Simpsons decreases dramatically faster. In fact, when we double n, left Riemann roughly cuts error in half, which is a huge improvement. Think of this like upgrading a camera. Some cameras improve image quality slowly when you increase resolution. Others improve dramatically. Simpson's rule is that the high-end camera. Small increases in resolution give you much better results. And the reason why all this matters is because in the engineering and physics world, we often need to measure curved paths, for example, road and bridge designs, roller coaster tracks, satellite orbits, and motion of objects in physics. Often there are no simple formula, so numerical methods are essential. This experiment shows that Simpson's rule is the most effective choice for this type of problem. Overall, this project demonstrates how mathematical theory matches computational results. And as we increase resolution, like this line right here, accuracy improves. And Simpson's rule consistently outperforms the other methods in both accuracy and efficiency.